This morning I have the distinct pleasure of introducing the keynote speakers. The first speaker is someone I've known for a long time, and I think everyone here probably already knows him too, but I will continue with this introduction nonetheless. Marcus Knudsen is from Sandia National Laboratories. He's a senior scientist and a fellow of the American Physical Society. He received his PhD in physics from Washington State University in 1998, and he joined the Sandia team right after that. Marcus's career includes research in high energy density physics and material dynamics under extreme pressures and temperatures. At Sandia, he led a team in developing a novel flyer plate capability using a magnetic loading technique that has since been applied to many important scientific and programmatic problems. Marcus is the Sandia point of contact for the Stewardship Science Academic Alliance program and oversees the Z Fundamental Sciences program. With that, Marcus, it's all yours.
Well, thanks, Ralph. So I'm doing my best Gabe Shipley impersonation today, since he originally was going to be the keynote speaker, but he decided to go elsewhere this week. So I thought what I'd do is just give you an overview of some research highlights from the Sandia Z Accelerator. And I stole a lot of these slides from Dan Sinars, who is our center director. He gave a talk recently at the Division of Plasma Physics conference, where he kind of highlighted some of these recent accomplishments. And really, truly, this is an exciting time, I think, to be in pulse power research. So Z is the world's largest pulse power facility, and we're currently doing a lot of work in fundamental science, use-inspired science, and applied mission science. And over the last decade or so, we've developed several platforms that allow us to, it's truly as a multifaceted facility. So we're doing research in inertial confinement fusion, so I'll show some highlights from that. Dynamic material properties, and we're also in radiation science, so we can do radiation effects sciences, but we can also do some interesting things in using the radiation source to do opacity, and so I'll show some highlights from that. And we really do think that over the next decade we're going to be solving some interesting science problems. It's kind of interesting when you think about the fact that the Z facility was built in the mid-'80s as an ion diode. In the mid-'90s, it was converted over to a Z-pinch facility. We did an upgrade in 2006, 2007 timeframe, and even today, we're still setting records for X-ray energy outputs, pressures that we can achieve. So even a 15-year-old facility since the last upgrade, we're still setting records, and so we think the outlook is really promising over the next decade. And then we're just starting laying the groundwork for the next generation pulse power facility, which is something that we're looking in the kind of 2030 time frame for that to become operational. Just last year, we got approval from NNSA to work towards critical decision 0, which is basically the first step in this process towards designing and building this facility. So we're pretty excited about that. So the facility sits at Sandia National Laboratories. Sandia is a federally funded research and development center, and Z actually touches on pretty much all of these areas of work that we do at Sandia in advanced science and technology, nuclear deterrence, national security programs, energy and homeland security, and global security. Like I said, we kind of touch on all of those at the Z facility. So Z, this is just kind of an overhead shot of what we call Tech Area 4. That's where the Z facility sits. So it's in this building right here. Right next to it in this building is Z beamlet, which was actually the prototype beamlet for the NIF laser. When Livermore was done using that, we were able to bring that over, assemble it here in this facility. You can see we've got a little causeway here that allows us to direct that beamlet into the Z facility itself, and we can use that for diagnostics, doing radiography type experiments. We're also looking at doing X-ray diffraction, and then we also use it as a heating source for maglev experiments as well. So if you peel the roof away, you can again see this is where the beamlet laser sits. This is that pathway into the center section of Z. We also have several target chambers where we can do standalone kind of laser-driven experiments using beamlet when it's not in use on Z. So how does pulse power work? Pulse power, we basically store a large amount of energy, and I'll show you on the next slide an actual cutaway of Z. This is we use Mark's capacitor banks to store that energy, and then basically the facility is compressing that electrical energy in both space and time. So it's stored on the outer perimeter that's directed inward towards the center of the machine, and as that electrical pulse is propagating, we use pulse-forming lines and fast switches to basically shorten it in time, right? So in the, at the beginning, we typically, it's about a 4-minute charging cycle for the capacitor banks, and in the end, we deliver about 100 nanosecond pulse to a load at the center. So here's that cutaway of Z. Some of you were able to tour this last fall. To give you a spatial scale here, this is about 110 feet in diameter and about 20 feet in height. So this section here on the outer perimeter, this is where the Mark's capacitor banks are. As I said, over about a 4-minute time frame, we charge this up. We can store around 20 megajoules of energy. And this is really the largest pulse compression stage is right here. So these capacitor banks are charged in parallel to 90 kilovolts or so. And then before we discharge them, we erect these capacitors in series. So we go from 90 kilovolts to about 5 or 6 megavolts. And when those capacitors are discharged, we go from a 4-minute charging cycle to about a 1 microsecond electrical pulse that comes out. That pulse goes down these transmission lines where we have a series of laser-triggered gas switches, and we also have some water switches that are self-braking. Those provide additional pulse compression down to, like I said, roughly 100 nanoseconds. Although in some experiments, particularly for materials, we want actually a longer pulse, and so what we do is we stagger the triggering of these laser-triggered gas switches so we can shape the pulse in a very precise way and deliver that to the load. And as I said, the load sits in the center section here. This is about 10 feet in diameter, and the load itself is typically kind of on the 1-inch scale or so. And Z, pulse power is actually fairly efficient. So of this 22 megajoules of energy that we're storing in the capacitor banks, we deliver roughly 2 to 3 megajoules of energy to the load itself. So roughly 10-15% efficiency, which is actually quite good. So Z is one of kind of 3 flagships facilities in the ICF program, along with NIF and at Livermore and the Omega Laser at Rochester, the Z facility here at Sandia. And as I said, we've kind of developed over the last 10 or 15 years multiple platforms where we can do kind of a wide faceted range of experiments. And I'm going to focus on these 3 areas today. So I'll start off with inertial confinement fusion, talk a little bit about dynamic material properties loads, and then finish up with the radiation science. So there were some talks yesterday that alluded to the maglev platform. So this is the magnetic liner implosion fusion concept. And this basically relies on 3 components. So we have an external magnetic field that we induce around the load, which is this kind of cylindrical load here. Again, size scale, this is of order 6 to 10 millimeters in height. So what that does, that pre-magnetization, is it reduces, during the implosion, it reduces electron heat losses and traps these particles. It basically takes these particles and they kind of ride these magnetic field lines. So you go from this kind of random motion here to something that's much more defined. And so this is helpful in that, as I said, it reduces that electron heat losses and increases the efficiency. Now, before we implode this cylindrical liner, we bring Z beamlet in to preheat the sample. And what that does is it ionizes the fuel that will lock in the B field during the compression. And what that really does is it relaxes the requirement that you have for the compression ratio. So instead of having to go to kind of ridiculously large compression ratios, we can relax that requirement and still do efficient ICF experiments. And then the final stage here is we run the current. We discharge up to 20 megamps or so of current along this cylinder. The J cross B forces then cause that to compress and stagnate on axis, and this is where we get PDV work to heat the fuel, and we also get some flux compression. So the magnetic field that we impose here that's trapped is flux compressed as we stagnate. And then at stagnation, that's where we see all this kind of kinetic energy being converted into X-ray energies, and we get several keV temperatures, and we can induce nuclear or fusion reactions. So over the years, we've kind of evolved the platform. So this is what it kind of looked like back in 2014 at the start of this program, kind of what it looks like closer to today. So that induced magnetic field, you can see these toroidal coils here. So we have a separate pulsar that delivers a several microsecond electrical pulse that basically provides then what in the time scale of these experiments looks like a static magnetic field. And then we have the liner itself in the center here, and that's where the implosion occurs. Now, if you look at the early designs, to be able to get a reasonably uniform magnetic field, we had the coil on top and bottom here, and so we had to extend the load up into this region. This increases the inductance of the machine or of the load. It kind of decreases the coupling of that energy. So with this type of design, we were kind of limited to only around 16 megamps of current. And you could kind of see here, this is the types of stagnation pressures that we could generate and stagnation temperatures. We're down in this range here. We did some experiments where we relaxed the requirement for the uniformity of the field that we're generating, went to a single coil design, so we got rid of that bottom coil. That allowed us to reduce the inductance of the overall load. We get better coupling efficiency, so we could get up to 20 megamps of current, and you could see how that drives the stagnation pressure and temperatures up. And then even more recently, we've gone to cryogenic cooling of the fuel. That enables us to have a thinner laser entrance hole. This gets back to Stephanie's talk yesterday with the little flap. We have to deal with getting the laser through that film, and so if we can go with a thinner film, that improves the coupling of the laser. It reduces the amount of mix, and you can see that we got even higher stagnation pressures and temperatures. And this is kind of about where we can go on Z. So looking ahead to a next generation pulse power facility, we've done a lot of work looking at scaling, some analytical scaling arguments for how the stagnation pressures and temperatures and yields go with current. And so we have these kind of empirical scaling relationships. So if you start looking at, okay, what could you do with a machine that can deliver more energy, more current? With the existing designs that we have, you could ask the question, what current would we need to get up to kind of a megajoule type yield? And if you ignore alpha heating, the current designs are kind of on the order of kind of mid 40 megamps. We do have some optimized target designs where we can reach that at even lower, say around just over 40 megamps. And if you push it even higher, some of these designs, you could at 60 megamps, you could generate tens of megajoules of yield. And so that's one of the things that we're looking at with the next generation pulse power facility. The architecture, the exact architecture that we would be pursuing is still kind of a point of research at the moment. We're in the process of collecting the requirements for the facility, but what we're looking at is something that would be coupling of order 10 megajoules of energy. So as I said, right now Z is coupling around 2 to 3 megajoules. So ultimately, we're looking at trying to couple around 10 megajoules of energy, and that would get us into the regime of a megajoule to a few megajoules of yield with this concept. So I'm going to switch gears now and talk a little bit about the dynamic material properties type experiments. In these experiments, this is showing a typical load that we would use. So here we've got, this is actually a cathode that's coming up through an opening in the upper anode plate. This is an anode material here, and we have this small gap. It's typically about 1 millimeter between the two. And so we're pumping all the current from Z into that one little feed gap, and that basically creates a large magnetic pressure that blows these panels outward. And as I said, we use the laser triggers to tailor the current pulse so that we tailor the pressure that we're applying to this very precisely so that we can do some interesting materials type studies. Again, spatial scale, this is typically around 4 centimeters or so in height and about a centimeter or so in width. And we've got two kind of workhorse platforms. One is a flyer plate platform where we basically use around a 300 to 350 nanosecond long pulse to supply a magnetic impulse that launches one of these plates at high velocity and impacts a sample, and we do a more traditional plate impact kind of shockwave experiment. Or we do an experiment where we tailor the pulse. We can stretch it out to around a microsecond or so in length, and we precisely tailor it so that we launch a stress wave in a material, and as that stress wave propagates, it actually evolves because the wave speed is a function of pressure. So as that propagates, it tends to steepen up to form a shock. And if we look at the evolution through different thicknesses of material, we can back out the sound speed as a function of pressure and get material properties out of those types of measurements. So the first platform, as I said, we typically have about a millimeter gap here. This is roughly a 1 to 1.5 millimeter thick plate. We'll use the magnetic pressure as an impulse to accelerate this. Accelerations are typically around giga-Gs, like 10 to the 10th Gs. We can accelerate this plate to tens of kilometers per second over roughly 3 to 6 millimeters. So that's kind of the spatial scales here. We impact the sample, that generates a large shock, and then we can do a kind of a standard shockwave type experiment. We've also looked at launching kind of tailored plates or composite plates. So we can electroplate copper on an aluminum surface here. So the aluminum surface essentially is what carries the current. This copper plate, what it allows us to do is put in a very well-defined pressure pulse. So we get a shock that runs into the material. It also runs backwards into this copper. When that shock hits the copper-aluminum interface, it reflects back a release wave, and that's what this is here. So we have a well-defined pressure pulse with a very well-defined pressure release. Using this type of loading, we can actually measure the sound speed of materials at pressure. And so here's an example. This is actually from a recent fundamental science project with the Carnegie Institute of Science was the collaborator here. And they were interested in bridgemanite, which is a high-pressure polymorph of MgSiO3. So it's a mineral that's relevant to planetary science, earth science. And what the question they were trying to answer is, where does bridgemanite melt on the Hugonio? How hard do you have to hit it for it to melt? And if you just look at the pressure density plot here, here's the data. There's really no clear indication of where melt occurs. But if you look at sound speed, it turns out when the material is solid, it can support an elastic wave that travels faster than the bulk wave. When the material starts to melt, you lose that ability, and so your leading wave velocity drops down to the bulk, and so you can very clearly identify the onset of melt. And what they found in these experiments is that the bridgemanite has an extraordinarily high melt temperature at high pressures. And so they've used this data then to look at the structure of various exoplanets, and it's kind of a busy plot here, but the takeaway is they looked at a bunch of different exoplanets, and based off of this work, they had identified a subset of 7 kind of super-Earths that are interesting in that they had similar ratios to Earth of iron, silicates, and volatile gases, and also interior temperatures that would be conducive for conductive, which is conduction, which is necessary for magnetic fields, which is something that is required for possibility of life. And so, they took from this group of exoplanets, they were able to identify ones that would be worthy of further study to see are they potentially habitable. As I mentioned, we can also kind of tailor the current pulse and do experiments where we ramp compress. This allows us to get to high pressures and stay solid. So this is some work that was done. It's actually part of a tri-lab effort that was looking at the strength of tantalum. So material strength is basically the ability of a material to withstand deformation. It's very important, quantity to kind of understand how materials behave at high pressures. And so there was a tri-lab effort to look at tantalum using various different platforms, different methods for measuring strength. On Z, what we do is we do what we call ramp compression and release. So here's the typical current pulse that we would impart into a tantalum sample. So you can see here we're looking at around a microsecond or so current pulse. And again, we achieved that by staggering the triggering of the gas switches. And you can see the result of, if we propagate this through tantalum, it turns out the shape of the peak here tells us something about the strength. And again, that's because this release wave is going to be traveling at an elastic wave speed, which is faster than the compression wave. And so with strength, it kind of, this wave sort of eats itself, if you can think of it that way. And so we can back out from this material strength. And so we did a series of 11 different experiments with 15 different measurements. And we're able to get strength measurements up to around 3.5 megabar. And you could see, based off of just the analytical analysis and also, a Bayesian type analysis where we're taking this data set, treating this entire data set in collectively to back out strength. In both of these analysis methods show that the strength of tantalum is quite a bit higher than some of the models that we have out there. And so this is, again, very useful information for modelers as they look at material strength at high pressure. And then finally, I'm just going to show one slide where we're looking at combining these techniques where we can do what we call a shock ramp type experiment. So a shock ramp experiment is kind of a hybrid where we have a longer pulse that we're driving the load with, and we put a small gap between the electrode and the sample. And what we do is we tailor the current pulse so that we can launch the electrode across that small gap, will impact the sample, and that generates a shock that propagates through the material. And then we follow that with additional current increase, which basically ramp compresses. So in this case, we took cerium, which is a metal that has a relatively low melt pressure, and we sent about a 20 kilobar or 20 GPa shock through the material. That was enough to dynamically melt it. And then we come back and ramp compress it and drove it back into the solid. And what we saw when we looked at the sound speed as a function of pressure effectively is that we would see this little kink here. And what that was indicating is that we were seeing an elastic behavior in that wave speed, which again is indicative of a solid. And so we were identifying that this material was dynamically melting and then refreezing as we recompressed it. And so we're continually evolving these platforms to access wider range of phase space through pure ramp compression, through shock ramp compression, and shock compression. So the final area I'll talk about is radiation science, where we can use these types of wire arrays to generate large amounts of X-rays and do some interesting experiments with that. So here what I'm showing is a typical Z-pinch, if you will. So it's an array of small diameter wires. And when you run current through these wires, they basically blow off into a plasma, and you generate a magnetic field that kind of encases this plasma. And the J cross B forces basically implode this on axis. So you get a large amount of kinetic energy that at stagnation transforms into heat and X-rays. And so this is a very effective X-ray source. And there's a fairly long-standing fundamental science consortium. It's called ZAP. It's the Z Astrophysical Plasma Project, where they use these types of sources to address interesting questions related to astrophysics. And they can do these all on the same experiment. So you can look at, like, on end on, you can look at the radiation coming out of the end of this dynamic hohlraum, and which can get you to very high temperatures. And you can ask questions like, what is the opacity of iron at conditions that are relevant to the convection zone of the sun? You can also put samples off to the side here. So here's a silicon foil that's being exposed to the radiation coming out the side. And you get to a little bit lower temperatures, but you can ask interesting questions related to accretion disk physics. You can also put gas cells that have, say, hydrogen or oxygen, expose that to the radiation, and ask some interesting questions that are relevant to white dwarf physics. And as I said, this can all be done on the same experiment. And so there's been a long-standing fundamental science program, with partners at University of Texas, at Nevada, Reno, Ohio State, West Virginia, looking at doing these types of experiments. And I'm going to focus on the iron opacity here. All right. So the iron opacity, there's been kind of a long-standing disagreement between the solar and structure interior models and helioseismology data. And the question is, what is that? What's the source of that disagreement? And so this project set out to ask the question, is opacity uncertainty the cause for the disagreement? And so what they set out to do is measure our iron opacity at conditions relevant to the convection zone boundary. And the way they did that is they took radiation from one of these dynamic hohlraum sources end on and exposed a sample that looks something like this, where you've got a half moon of just plastic, and then you've got, on this side, you've got a sample of interest that's encased in that plastic. So you look at the transmission through the plastic and through the plastic and the sample, and you can look at the opacity of the material that's encased in that plastic. And this is the result of those experiments for iron, and you can see that the data here compared to some of the models, there's quite a bit of a difference here, right? And it turns out this difference accounts for about half of the disagreement between the helioseismology and the various models. So this was actually, got quite a bit of interest. There was a Nature paper that was published as a result of that. Subsequent study, they wanted to really, look at this in detail and say, well, is this different, or disagreement here, systematic, or is this, is it a problem with the experimental platform, or is this actually a real difference? And so they looked at chromium, nickel, at similar conditions, and you can see in those cases the measurements and the models are in pretty good agreement. So it does not appear to be a platform systematic issue on the platform. I'll also point out that trying to resolve this difference, they're now doing similar experiments on NIF, looking at the opacity at similar conditions, again to try to rule out any kind of platform issue itself. So that was a fundamental science example. The Bridgmanite I showed was also a fundamental science example. As was pointed out earlier, I kind of managed the fundamental science program at Z, so I wanted to put a little plug in for that. We're entering our, I think, 12th year now as an official fundamental science program. And during that time, we've had 118 dedicated experiments, which works out to be about 7.5% or 8% of all the shots that have been done over the last 12 years. So it's a growing program. You can see a list of collaborators here. Over the years, we've started new projects. In fact, this one right here, just last year, this is a magnetic reconnection platform. So it's a brand new platform on Z where they actually, instead of a imploding wire array, you can imagine having two exploding wire arrays sitting next to each other. So this plasma, instead of being compressed inwards, it's being blown outward, and you've got a region in between here where these two plasmas are colliding, and that's setting up conditions where you can have a magnetic recombination or reconnection. And this was fielded for the first time last month, and they were successfully able to show that they could split the 20 megaamps evenly across these two loads, so 10 megaamps on each one of them, generated a layer that appears to be a reconnection, and so they were very excited about that. And as I said, we're continuing to evolve new platforms and continuing to figure out new ways or new experiments to do on this machine that's a couple decades old now. So this is actually a really good opportunity for academics to get involved in Z experiments. Every year we have a proposal process for time on through this program. We just actually opened up the CY22 call for proposals last week. The timeline here is that the proposal opens, the call opens in mid-June. It closes in September. In between, we have a fundamental science workshop, and I'm excited to go back to an in-person workshop again this year. So August 2nd to the 5th, we're going to meet at the Hotel Andaluz in downtown Albuquerque. And this is a great opportunity for people to sit down with Sandia researchers, kind of develop their ideas and their proposals so that they can meet this deadline of mid-September. We then go through some facility reviews just to look at the feasibility of the experiments, and then we have an external review panel that will evaluate the proposals, and then they give us recommendations on experiments to provide awards for. And then in mid-December, we distribute those awards, and each call is for 2 years worth of experiments. So the experiment dates here would be mid-July of next year through the end of June of 2025. So I would encourage anybody who's interested in this program to come to the Fundamental Science Workshop and sit down with some Sandia scientists and come up with some interesting ideas to propose for this program. And as I said, I hope I convinced you that the Sandia Z Accelerator is an interesting and unique place for doing HED science. We can get it to multi-megabars in material studies. We have a copious amount of X-rays for doing radiation, both radiation effects and also looking at, say, opacity and things of that nature. Interesting plasma physics experiments. And one of the things that we really are proud with at Sandia is that we've got a very strong integration between experiment theory and simulations that help us to really advance this platform. So with that, I'll take any questions you might have.